Hello. In this video, I want to talk about Kepler's laws. Specifically, there are three laws that Kepler's had discovered. Kepler's law number 1, number 2, and number 3. The concentration is going to be on Kepler's third law, which is the one that is mathematical. So let's begin. Kepler's first law basically says that all the planets in the solar system orbit their parent star, for our case, our sun, orbit their parent star in an elliptical path. Okay, and I think we talked about that. What is an ellipse? So the ellipse basically looks something like an oval shape. It's an elongated shape that looks like this. I'm trying my best to draw it with my pixel. I can do it easily with a chalk or pencil. There we go. It's not perfect, but that's basically how an ellipse would look like. It has, think of it like it has two axes. One axis here is called the major axis because this is like the longest axis in the ellipse, and then the shortest one is here. It's called the minor axis, if I can draw it though. There we go. So this point right here is called the center point, and so from this point right there, the extreme right or left of the ellipse to the center, we call that the semi-major axis. This one here, semi-major axis A. So A is the semi-major axis. Semi means half, because this is half the major axis, the longest axis. And then the vertical one from the center to the top there is called B. It has a symbol B, and it is the semi-minor axis. Okay. Okay. So in addition to that, let me just take out the A here. In addition to that, so we have one point, it's the center of the ellipse right here. In addition to that, there are two other points that are located somewhere here. They are equidistant to the center, and each of them is called the focus. Okay, it has usually in geometry the symbol capital F for each of them. The distance between the center to the focus is C. Okay, and then there is a geometric relationship that links A, B, and C together, which is not our concern. You're more than welcome to look up the geometry of the ellipse. There's a lot of interesting geometry that the ellipse is involved in. So anyway, this is not our subject. So what Kepler's first law basically says is that the planet, let's say our Earth, or maybe the moon around the Earth, or whatever, something orbits something else. It basically, the Earth, here is the Earth, for example, it's moving around the sun such that, let me just eliminate those things, such that the sun is located at one of its foci, right here. Not in the center, it's right at the focus, one of the foci, not both of them, of course. So let's say the sun is right here, okay? So this is the sun, and here is, let's say, our Earth. So it's going around it. So the Earth goes around it in that fashion. Okay. So that's Kepler's first law. So Kepler's first law says the sun, the Earth orbits the sun at one focus, at one of the foci of the ellipse. Okay. Okay. The second law, basically says, let me just write it down and I'll explain it to you. Kepler's second law. It says the Earth sweeps equal areas in equal time intervals. Okay, in equal time interval. What that means is the following. Let's say, for example, here is the elliptical path of the Earth around the Sun. Okay, let's draw one very quickly, just like, say, this one. When I draw it fast, I do a better job. So let's say, for example, here is the Sun right there. Okay, and let's suppose that the Earth today is right here. Okay, for example, and it is going in this direction. Okay, let's say I tag the position of the Earth right now. Okay, so here is the distance between the Earth and the Sun. And now let's say I tag the position of the Earth for the next 2 weeks. So now after 2 weeks, suppose that the Earth is here right now. Okay, after 2 weeks, for example. I'm picking any random interval. Okay, it could be 2 months, whatever. So let's say this is 2 weeks. And what I want to do, I want to connect the distance between the Earth and the Sun like that. And what I want to do is I want to calculate the area that the Earth have swept within 2 weeks. Again, this 2 weeks is a random, choice. It could be anything else. Now, later in the year, let's say after a few months, the Earth's location is right here. Okay, and I want to do exactly the same thing. So I would tag the location of the Earth, say right there, and then I would wait another 2 weeks. And then now, after 2 weeks, the Earth is here. Whoops, hold on, I'm having difficulty. There we go. So after 2 weeks, let's say the Earth is right here. And so if I would measure again the area swept by the Earth within 2 weeks in this new location or any other random location, I will find that those two areas are actually equal to each other. Okay, which is really remarkable. So those two areas equal areas in equal time interval. Okay, it's a very basic law, but it's an amazing law. I mean, no one knew that. Of course, after 100 years or so, Isaac Newton comes in, and he is the father of physics, and he comes up with a new concept called the conservation of angular momentum. And it's basically this law, this geometric law that Kepler didn't know anything about physics or any the laws of physics. They weren't yet invented or discovered yet. We had to wait another 100 years for Galileo and Newton to come in and to create this new branch of science, what we call today physics. And during that time, he didn't know anything about what we call angular momentum, but this is basically the law of angular momentum. Okay, good. And then they get the third law, which is the one that I want to talk about. And like I said, Kepler's third law is more of a mathematical law, and it basically says, let me just put in the formula first. It says there are two versions for it. Here is the version that we're going to be studying more in our course in astronomy, which basically says that the period squared is equal to the semi-major axis a cubed, or radius cubed. Okay, that's Kepler's third law. This is kind of a light version, but that's the version that we're going to be studying in our course. So here, period, P for the period, and period means the time it takes the planet, the time it takes the planet to orbit the sun. Okay, for our case, for example, Earth, how long it takes Earth to orbit the sun? 1 year, you see what I'm saying? Or we can say 365 days, or 3.14 times 10 to the 7 seconds. I always remember this number. It's easy to remember, by the way. Look at that. 3.14 is pi. So pi times 10 to the 7. It's kind of an easy number to remember. How many seconds in a second in a year on Earth is Approximately. This is not exactly that, but it's a good approximation. Anyway, so that's basically what we call the period. So we can write the period in terms of years, in terms of days, in terms of months, 12 months, or in second and minute and whatever. Okay, and then you have the A here is the semi-major axis. For all practical purposes, we can just think of it as the radius of the orbit, okay? Because the deviation from being a perfect circle is very, very small. Anyway, so this is basically the semi-major axis or the radius of the orbit. Okay, so one more thing. In order for this formula to be valid, there is a condition on it. And the condition is that the unit of the period must be in years, okay? Must be, okay? You cannot use seconds or days or months or whatever. It has to be in years in order for this formula to be valid. And then the semi-major axis, or the radius of the orbit A, semi-major axis, it has to be in AU. And as you may remember, AU is what is the average distance between the Earth and the Sun, right? It's equal to 1.5 times 10 to 11 meters. This is equal to AU. This is the Earth here, specifically the Earth. Okay? Just to remind you, let me go back to the formula sheet. Always keep the formula sheet handy, guys. Here it is. And 1 AU is right there. How do I magnify it? There we go. As you can see right there, right here, 1 AU is 1.5 times 10 to the 11 meters, this is the average distance, not the precise distance. That's the average distance between the Earth and the Sun. Okay. Of course, this also can be also written in kilometers. 1.5 times 10 to the 8 kilometers. Remember, 1,000 meter is one kilometer. Okay. All right. So that's the condition for this formula to work. Keep that in mind. This is very important. So the condition is that for this formula right here. So the condition is that the period must be in years, and the semi-major axis, or the radius of the orbit, has to be in AU. Okay. So let me give you an example. I have some examples here in my notes, and there are some examples that you will notice under the homework presentation. And you may see it also on the exam. So here's an example. Example 1. It says we have a planet found with orbital period of 64 years. All right. Now it says estimate its distance from the Sun. Okay, so we have a planet. So what that means, here is the Sun. Okay, and we are observing it from our Earth, and we notice there is a planet right there. This is the planet. And the distance between the planet and the Sun is, oh, I'm sorry, we don't know what it is. I'm sorry about that. So we don't know what A is, but we have been observing the planet, and we discovered that the period of this planet, P, is 64 years. Now, with this information, if we know that the period is 64, how far is it from the Sun? You see what I'm saying? Planet. Okay, so what we do, we go to Kepler's third law, and you definitely need to use the calculator. So bring out your calculator and let's calculate it together. So the Kepler's third law says period squared equals a cubed. I am solving for a cubed, so I like to put the a cubed on the right-hand side. Again, that's just my taste. And then what I would do, I would plug in what I got. So P squared, remember P is equal to what? Is equal to 64 right there. So I'm going to put 64 I beg your pardon. What am I doing? This is, yeah, that's right. Am I right? Yes, I'm sorry. Okay. So we have 64 quantity squared. And then I'm going to use my calculator. I'm going to bring the calculator that I have in my PC so you can see what I'm doing. You remember this calculator? We talked about it in a previous video. So I have 64, and then to the power of, I can use the power right there, squared, and there we go. It will give me quickly the number. It is 40. Whoops, it disappeared. Darn it. Come back. Okay, 4096. Okay, so we have 4096, and that's a cubed. Remember that, right? So what is a? It's basically the cube root. So I have the cube root of 4096, and hopefully your calculator has a cube root, or there are other ways to do it. You can also use y to the let's see if there is another way of doing it here. With this calculator, that's the only one, but you can use x to the power of y right there. But that power of, what I'm trying to say is this. Again, you can use your own calculator for that. So you're going to be 4096 to the power of 1/3, right? Or 4096 to the power of 0.333. I like it in decimals because it's kind of easy to enter it into the calculator, so I'm going to do it that way. So I'm going to go like this. Whoops. Let me move it here. So here is the number that we're going to be using. So basically, the way you do it is 4096 to the power of, right there, and then 0.3333, but a bunch of threes if you want to. The third is kind of an irrational number, and that will give me the answer. There it is, 15.999, which basically 16. You see what I'm saying? So it's basically 16. So the answer here, it's 16. 16 what? 16 AU. You see what I'm saying? You got it? So we go back to this diagram here. So here is the sun. Here is the planet. We discovered that the planet, it takes the planet 64 years to go around the sun. How far is it? It's 16U, which means 16. In other words, if the Earth is here, which is 1 AU right there, the planet is way out there 16 times further. You see what I'm saying? Okay. One more. We have here, it says, how far is a planet from the sun? I'm sorry, I need to read it here from my notes. Oh, compared to the Earth. Okay, and basically what we are doing here, let me just, okay. What we are doing is, I'm looking at my notes here. So basically we have Pluto. So the period of Pluto is 248 years. And we want to know how far is Pluto. Okay, and then we want to compare it to the Earth. Okay, so how do we do it? Well, basically we use the same formula. So we have here p squared equals a cubed, and I am solving for a. I like to put it on the right side, like here, on the left hand side, and that'll be p squared like that. Remember the period here is given to us in years, so I'm going to plug it in there. 248 quantity squared. So I'm going to square the period. Let's do that. So I have here, let me just delete everything. Okay, so we have 248 to the power of squared, or you can just directly square it, Anyway, so we got 61504. So we got 61504. And then we take the cube root of that. And the cube root, as I told you, you simply put it to the power of 0.33. If you have a primitive calculator, that's the one like the one I have. So that's to the power of 0.333. Again, you may have a dedicated button for the cube root, so you can do it, so you don't have to bother with what I'm doing. So anyway, let's do that. So in this case, I will have, okay, I think I got this number, so I can just go to the power of 0.333, and the answer would be 39 more or less, or 39.3. So it will be something like, let's say, 39 AU. Okay, so 39 AU. In other words, Pluto, let's make a picture of that. So Pluto, so here is Pluto right here. And here is our sun. And our Earth is somewhere here. Is only 1 AU from the sun. Pluto is way out there at a distance of 39 AU. It's actually 39.5 AU, if I remember correctly. Anyway, that's just the rounding thing. And this is Earth here. Okay? So how far is it compared to the Earth? 39 times, almost 40 times farther. Okay? All right, one more. I'm looking for something with a different twist to it. All right, one more. Hopefully those problems are not going to get any harder than that. It's kind of a simple formula. So here's another one. It says if an asteroid has an average distance from the sun of, what is that? Oh, 4 AU, okay. What is its orbital period? Okay. Question mark. All right, simple problem, same thing. We just use the same formula. So we have p squared equals a cubed. What's given to us? So what's given is a is 4 AU. It's 4 times as far away from the Earth. And we basically simply plug it in there. So that's going to be 4 AU quantity cubed. 4 cubed is 4 times 4 is 16. I can do this in my head. 16 times 4 is 64. So we have p squared equals 64. And therefore, p, I don't need a calculator, square root of 64. And that's, so the period is 8 years. Okay? What that means, now what does that mean? It means, let's go back to so here is the sun. Okay? Here is the asteroid here. And it is 4, what is it, 4 AU? I forgot. Yeah, 4 AU. So we have 4 AU a distance. So this asteroid is going around the sun. You see what I'm saying? I'm not doing it right. Hold on. So it's going around the sun like this. And how long does it take it to complete one cycle? That's basically the question. You know, how long? That's the period. Well, it takes it 8 years. 8 Earth years. Okay, so that's 8 Earth years. You see what I'm saying? Okay. All right. The last thing I want to talk about is there is a different version for the period. And I mean, Kepler's third law and period and the semi-major axis. That version is more common or more used in physics because it's based on Newton's gravitational law. I don't want to go through the derivation because it requires that you know basic physics, and I'm assuming some of you have not taken physics, so I'm not going to go over it. But basically, just a refresher for you, you know the Newton's gravitational law. Basically says if there are two masses, I have a video on that if you remember, and the distance between them is r, and then let's say we call that mass 1 and this is mass 2, so there will be a force between them. There is a force of attraction, there is a tendency for them to come together, and this force is equal to g, which is the gravitational constant, the universal gravitational constant, times the product of the two masses divided by their distance squared. Okay, so Kepler's third law can be derived using this formula right here. Okay, but again, that requires some knowledge of physics that is beyond the scope of our course. It requires something called a centripetal acceleration. Anyway, so when you work it out and then you derive it, you actually come up with Kepler's third law using Newtonian law, using the Newtonian gravitational law. So third law is this one. This is the more common one that's used by physicists, and that basically, let me use the same symbolism. So the period squared is equal to 4 pi squared over g mass of the sun times a cubed. Okay, there it is. This is basically, as you can see, nothing, I mean, there is the p cubed and there is the a cubed. The only thing is that there is this constant. See, that's just a constant. The mass of the sun is a constant. The g is a constant, you know, the universal gravitational law, which is 6.67 and negative 11, and then you get 4 pi squared, you know. So the whole thing is a constant. But the catch, the difference between them is this. You cannot use the period in years. The period here is in seconds by default, okay? And the a here, the semi-major axis, or we actually, in this case, we would refer to it as a radius, and that would be in meters. That's a must. Otherwise, this formula, again, there are different versions for different units, but this is how we do it in physics. So I want to give you a very quick example and show you how cool this equation is. Let's apply it to the Earth. As you know, what is the period of the Earth around the sun? 1 year, or we can say 365 days, or, what is the period of the Earth around the sun? Is 1 year, or we can say 365.25 days, or we can say 3.14 roughly. It's actually closer 3.15. Anyway, times 10 to the 7 second, and maybe 12 months if you want. You know, there's so many different units that we use, so you have to pick one unit. For this formula that we are using, if we insist on using the value of g that we know of, it's going to come out in second. You can see what I'm saying? And so what I want to do, I want to prove to you that this value right here can be calculated using this formula. Suppose I don't know anything about the Earth, okay? And I don't know, I'm an alien. I don't know how long it takes the Earth to go around the sun. But I know the radius of the Earth around the sun, this one. So can I predict the period? Yeah, we can do it. Let me show you how to do it. So let's do that. It's just kind of for fun. So here it is. So you go p squared equals 4 pi squared over, I want to show you the formula as I plug all that stuff in there. Maybe I'll just put it here. So it is g mass of the sun times a cubed. So let's put the numbers in there. So we have 4 pi squared divided by g is 6.67 times 10 to the negative 11 times the mass of the sun, 2 times 10 to the 30. All of that multiplied by the radius of the Earth around the sun, as you know, is 1.5 times 10 to the 11 quantity cubed. You see what I'm saying? So how do I know all of that? Again, you go back to your formula sheet, the one I created for you. They're all in there. It's right there. Right here, guys. There we go. The mass of the sun, 2 times 10 to the 30. We also know the, what else did we, the AU, which is how far the Earth from the sun, is right there, 1.5. Okay, so nothing, everything is shown in the formula. So now what I want to do, I want to use my calculator and plug it in, and hopefully we will get that from the number that we are, you know, for the period of the Earth around. Let's see, how do I do this? Maybe I'll just move it to this side, down this way. Hold on, I'm trying to keep it on the screen, the same screen. Hold on. There we go. Okay, there we go. So now let me take this calculator, put it within the screen. There we go. Hopefully you'll see all of that. There we go. Okay, so let me clean up everything. Hopefully I'm not going to make any stupid mistakes. Let's start. So I'm going to start with 4 pi squared. So that's going to be, you know what? Let me start with this one. I like to start with something with a power. So it's going to be 1.5, right? exp 11. Okay, and then what I want to do, I want to put it to the power of 3, right? So it's to the power of 3. So it's going to be x to the y 3 equals, we got that. Now I'm going to multiply it by pi squared, so times pi squared, and we got that. And then we're going to multiply by 4 equals, and we got this number, okay? Now, we still have to divide it by g, this one. So we're going to divide it by 6.67 exp negative 11. Remember, the negative right here. Negative 11 equals, and we got this number. Now I want to divide it by 2 times 10 to the 30. So divided by 2 exp 30 equals, and we got this big number. Let me put it in scientific notation, and it is this 9.99 times 10 to the 14, basically 10 to the 15. Okay, now remember, this is in p squared. Remember that. Look at this formula here, guys. It's p squared. See that? So I need to square root it. You know what I mean? So let's square root that. So square root this number, and there we go, 3.16 times 10 to the 7. Hopefully this is a familiar number for you. So let me write it down here. So P in this case is 3.16 times 10 to the 7 second. If you remember, I told you it is approximately, what is it? There it is right here. 3.15. This is more accurate, 3.15. So, I mean, because of the rounding, we get that. But this is pretty darn accurate. You can actually predict that using Kepler's third law. Okay, so those are the two versions that are common. The one, the former one is the one common in astronomy. If you want to use AU and years, you don't need to use this. What's nice about it, you don't have to deal with a constant like that. You just a cubed and p squared. But if you want to use seconds, something more accurate like that. So this formula comes in handy as well. Okay. Okay, that's it. That's all I wanted to talk about as far as Kepler is concerned. And please let me know if you have any questions. Bye-bye.